So from here on, let me focus on the Kepler potential, and we'll investigate the properties of the solution for the Kepler potential in a lot more detail. And I would like to focus at first on the case of total energy smaller than zero, so that we have bounded motion. So we are not in the scattering regime, but we are in the regime of bounded motion. And I would also like to assume that the conserved angular momentum is different from zero. So we do have this centrifugal term in the equation of motion that is non-zero. And remember, the potential has the form U of r is proportional to minus 1 over the distance, and that constant of proportionality I would like to call alpha. So we have the form, this is minus alpha over r, and alpha shall be positive. A first analysis that we can make is that we can try to determine the turning points in our one-dimensional problem, that is the minimal and the maximal distance of the body from the center of the potential. At the turning point, the time derivative of rho vanishes. Rho dot is zero. Therefore, at the turning point, we must have in our balance equation for the energy, we must have that the value of the effective potential at the turning point is exactly equal to the total conserved energy, E. Let's use the formula for the effective potential in the Kepler case. That is L squared over 2 times mu rho squared minus alpha over rho, and that shall be equal to E. Now you see, this is a quadratic equation for rho, so you can solve that in a straightforward manner as you solve quadratic equations. I would like to introduce 2 new constants to give the solution a particularly simple form. I would like to introduce a parameter kappa, and I define it as L squared, the conserved angular momentum squared, divided by reduced mass mu times alpha. And I'd like to define another parameter epsilon as the square root of 1 plus and then 2 times energy times kappa over alpha. Then solving the quadratic equation for rho, we get, as usual, in general we get 2 solutions, and these 2 solutions correspond to the minimal and the maximal distance from the center of the potential. And that solution can be written in the following form. 1 over epsilon, that parameter epsilon, times 1 minus kappa over rho is either plus or minus 1, where the plus sign corresponds to maximal distance. So if we, on the right-hand side, we take plus 1, then as a solution for rho, we get rho max. If on the right-hand side we choose minus 1, then as the solution for rho, we get rho min. And the left-hand side, that is a function of rho, and I denote that function as S of rho. So that's perhaps a slightly unexpected way of writing the solution. You can I suggested as an exercise for you that you simply solve the quadratic equation in the conventional way and convince yourself that the two solutions satisfy the equation below. The reason I write it in the form below is that will make it easier to understand the shape of the orbit and to do other analysis that comes afterwards. Yeah, in fact, let us next verify that indeed the orbits in the Kepler case are closed. So what we must verify, as we had seen when we discussed Bertrand's theorem, what we have to verify is that angle delta phi, so going from maximal distance to minimal distance and back, you will have rotated by some angle delta phi. We must verify that this is an integer multiple of pi. Remember in the energy balance, we have on one side we have E minus, so on the left hand side you have mu over 2 rho dot squared. On the right hand side you have E minus the effective potential of rho. It is possible to express the effective potential of rho in terms of this new function S of rho that I introduced on the previous page. So it is possible to write E minus the effective potential of rho in the following form. It's alpha times our new parameter epsilon squared divided by 2 kappa times 1 minus S of rho squared. Then let us use the general formula that we have for the angle delta phi. Let us look that up here. This is the general formula for the angle delta phi. So this is the formula that we have, the general formula that we have for delta phi. And now we use this expression here and insert it in that formula below. When we do that, delta phi becomes the square root of 2. Let me take the L under the square root, then it gets squared, divided by mu. We have an integral from rho min to rho max, d rho. And then we have a 1 over rho squared. And from the square root, we have the square root of 2 times kappa over alpha epsilon squared. And we have a 1 over square root 1 minus s squared. In the square root in front of the integral, we can introduce a factor alpha both in the numerator and in the denominator, and identify L squared over mu alpha with our parameter kappa. The alphas cancel out in the two square roots, but and we can replace in the first square root, we can replace this L squared over mu alpha by kappa. So we have a square root of kappa, and in the second square root we also have a square root of kappa. We can substitute in the integral. We can say d rho times 1 over rho squared. That is the same as d minus 1 over rho. Then we observe looking back at the previous page. When you take the equation, the last equation on that page, you look at the function on the left-hand side, s of rho. When you take the differential of that, ds. Now, epsilon and kappa are just constants, they're just parameters. So ds equals minus kappa over epsilon times the differential of 1 over rho. In other words, the differential d minus 1 over rho equals epsilon divided by kappa times ds. So this is ds times epsilon over kappa. Yeah? Using the function that we had introduced on the previous page. Of course, when we go from rho to s, we must also change the limits of our definite integral. When we are at minimal distance, rho min, you saw on the previous page that corresponded to that function s of rho being minus 1. So the lower limit of the integral is now minus 1, and the upper boundary of the definite integral corresponds to maximal distance, and that corresponded to the case where this function s of rho was plus 1. So we have now an integral from minus 1 to plus 1 ds epsilon over kappa. Yeah, then we still have the square root in front. Then we have a square root of 2. In the second square root, we also have a square root of 2. So we can combine that into a factor of 2. And then we still have here a square root of kappa. And from the second square root, we have square root of kappa over epsilon squared. And then we have 1 over square root 1 minus s squared. And at this point, you see that the two square roots of kappa cancel against the 1 over kappa. And the epsilon cancels against the 1 over square root of epsilon squared. So we are simply left with 2 times the integral from minus to plus 1 ds 1 over square root 1 minus s squared. Now this is one of the standard integrals that gives 2 times the arc sine of s in the limits minus 1 plus 1, and that equals 2 pi. So it's indeed a multiple of pi. In fact, it's 2 pi as claimed already in the context of Bertrand's theorem. So indeed, the orbits of the Kepler problem are closed. Now you know that the orbit is closed. Next, we would like to understand the geometric shape of the orbit. I had claimed that this is an ellipse, but I haven't proved that yet. So let us next look at the geometric shape. On the previous page, we calculated the delta phi after going from maximal to minimal distance and back. We can also look at the infinitesimal version of that and look at how the angle phi changes infinitesimally. We can do exactly the same substitution as on the previous page to find that the infinitesimal change in the angular coordinate d phi is ds, our function s of rho, ds, times 1 over square root 1 minus s squared. And by doing now an indefinite integral, we find that phi as a function of s is the arc sine of s plus some arbitrary constant c, and we can always choose coordinates suitably in such a way that this constant is equal to pi half. Then, inverting this equation, we have S equals the sine of phi minus pi over 2, which is the same as minus the cosine of phi. Then we can remember the definition of S of rho, and we find that kappa over rho equals 1 minus epsilon s, but s is minus the cosine of phi. So in fact this is 1 plus epsilon cosine phi. So let me draw this here. We have the x and y axes in Cartesian coordinates. We have our closed orbit, whose shape we have yet to understand. We have, for a certain point on this orbit, we have angle phi and distance from the center of the potential rho. And the equation on the left-hand side that we just derived claims that there's this, shows that there's a relationship between rho and phi, and this relationship is governed by, is described by this equation. So in the next step, we will have to show that if we have this relationship between rho and phi, this corresponds to an ellipse. Let me note at this point, even though I said at the beginning that I would like to focus on the bounded case, where we have closed orbit, we're not in the scattering regime, this equation here is independent of this choice. So this holds regardless of the value of the total energy. So it holds both for the bounded and also for the unbounded motion. Oh, let me add here in this drawing, just for completeness, the usual transformation law between Cartesian and cylindrical coordinates. So x equals rho times the cosine of phi, and y equals rho times the sine of phi. All right, let's continue and verify that this equation describes an ellipse. The equation on the previous page can also be written in the following form, multiplying the equation by rho. We find that kappa equals rho plus epsilon, and then rho times the cosine of phi, but rho times the cosine of phi is equal to x. In other words, epsilon times x minus kappa is equal to rho. We can take the square on both sides, and rho squared in turn equals x squared plus y squared. Using the binomial formula, we find that epsilon squared x squared minus 2 times epsilon kappa x plus kappa squared is equal to x squared plus y squared. We can take the epsilon squared and x squared on the right-hand side, combine it with the x squared, and we get 1 minus epsilon squared times x squared. And let me switch sides so that on one side we have x squared times 1 minus epsilon squared. Then let me also take on the right-hand side, or on the same side, the term 2 times epsilon times kappa times x. So we have 2 times epsilon times kappa times x. Then we have y squared And the only term that remains on the other side is the kappa squared. Okay, one thing I would like to do here is I would like to multiply all terms by 1 minus epsilon squared, and then we get here an extra squared. This is procedure number 1. And then I would like to divide by kappa squared, so I want to get rid of the kappa squared here. I get a kappa squared here in the denominator. Here instead of kappa, I get a 1 over kappa, and here I divide by kappa squared. Now next, let me define two different parameters. Let me define A as kappa divided by 1 minus epsilon squared, and B defined as kappa divided by the square root of 1 minus epsilon squared. With these definitions, the first term on the left-hand side simply becomes x divided by a squared. The next term is then 2 times epsilon times x over a. That comes from the first term in the 1 minus epsilon squared. No, sorry. No, that's it. Yeah. So this is the second term is 2 times epsilon times x over a. Then we can, from the right-hand side of the equation, we can take the epsilon squared to on the left-hand side. So we can add here an epsilon squared. And then finally we have the term with the y squared, but that term is now equal to y divided by b squared. And on the right-hand side, only the 1 remains. This is a binomial formula here. This is in fact x plus epsilon a over a squared plus y over b squared is equal to 1. And this I hope you recognize is the equation for an ellipse with the center displaced from the origin. So here's the formula that we derived on the previous page. If in the first bracket we simply had x over a squared without the epsilon a term, then this would describe an ellipse with the center at the origin of our coordinate system. Since we have the epsilon a in there, this means that the ellipse is displaced to the left. The center of the ellipse is displaced from the origin of the coordinate system by epsilon times a. So this distance is epsilon times a. Now a is one of the half axes. So let me denote this here. This is a. B is the other half axis. Let me indicate it here. This is B. This here is the center of the ellipse. And the orbit will look like that. Now the origin of the coordinate system, there is the so-called focal point of the ellipse. And epsilon, the parameter epsilon, which characterizes the displacement of the center from the focal point, which characterizes the distance between center and focal point, is also called the eccentricity of the ellipse. let me finally indicate sort of a specific point on that orbit and indicate the cylindrical coordinates phi and rho. I told you that that equation that describes the geometric shape of the orbit is valid regardless of the sign of the energy, so it's valid both for the bounded and the unbounded motion. What is then the difference in this geometric picture between bounded and unbounded motion? When you have bounded motion, then the focal point is inside the ellipse. And the eccentricity, epsilon, is smaller than 1. This gives rise to an ellipse. If, on the other hand, you have unbounded motion or scattering, well, then the equations that we derived are still all valid, only that then epsilon is larger than 1, and for the geometric shape, rather than an ellipse, this gives rise to a hyperbola. To see this distinction between bounded and unbounded motion, epsilon smaller and larger than 1, also recall the definition of this parameter epsilon. You see here, epsilon is that square root of 1 plus 2 times energy times kappa divided by alpha. Kappa and alpha are positive. In the bounded case, the energy is negative. So under the square root, you have an expression that is smaller than 1, and therefore the parameter epsilon will be smaller than 1. For the unbounded case, the scattering case, the energy E is positive. So under the square root, you have an expression that is larger than 1, so the square root itself will also be larger than 1. Yeah? So here you see mathematically that bounded and unbounded motion correspond to epsilon smaller and larger than 1. And then you see in the geometric picture, if epsilon is smaller than 1, then you see that the focal point is inside the ellipse. If epsilon is larger than 1, then it's no longer an ellipse actually, but then it's a hyperbola. So these mathematical results immediately give rise to Kepler's laws for planetary motion. Law number 1 and law number 2 are really trivial now, because law number 1 simply states that the planets move on elliptical orbits with the sun in one of the focal points, and that's what we just proved. So there's nothing more to say. Except for the fact maybe that Kepler states the sun is in a focal point. This is, strictly speaking, not true, because what is in the focal point is the center of mass of planet and sun, but the sun is, of course, much heavier than all the planets, and therefore, for all practical purposes, the position of the sun equals, to very good accuracy, the position of the center of mass. Yeah? So just let me write this down. Law number 1 says the planets move on elliptical orbits with the sun in one of the focal points. So here we have the sun, here we have the planet, and here we have the center of mass of the two, which, as I said, is practically identical or very close to the position of the sun. So the fact that the mass of the planet is much, much smaller than the mass of the sun implies that the position of the planet, the position vector of the planet in the center of mass frame, so in a reference frame where the center of mass is at rest, that this is approximately equal to the distance vector between planet and sun. And the position vector of the sun in the center of mass frame is approximately equal to 0. It's approximately at the center of mass. So that's Kepler's law number 1. Not much more to say about it. Kepler's law number 2 is the area law. The law number 2 states that in equal times, the ray connecting the planet with the sun sweeps over equal areas. And that is an expression of the area law, which we had learned is simply a consequence of angular momentum conservation. For this reason, the area law holds not only for the Kepler potential, but it holds for all central potentials where you have angular momentum conservation. So laws number 1 and number 2 are really straightforward. The only law of Kepler that requires a little bit more effort is law number 3. Kepler's third law states that the ratio of the period, or the time it takes a planet to go once around the sun, squared, divided by the semi-axis of the ellipse, cubed, is constant, or at least to a very good approximation, constant. It's the same for all planets. So how can we understand that law number 3? As a starting point, let's look at the area law. The area law said that the area swept over in per unit time, which is related to the angular momentum, the conserved angular momentum. It's the conserved angular momentum divided by 2 times the reduced mass. That this is constant. This is the infinitesimal expression of the area law, but let's now look at one complete orbit around the sun. If a planet goes around the sun once, then the area covered is just the area of the ellipse. So the area of the ellipse is pi times the product of the 2 semi-axes, A and B. By the area law, this must be this constant area covered per unit time times the time that it takes to go one time around the sun, which is the period, capital T. And using the expression for dA over dt, this is the period times the angular momentum divided by 2 times the reduced mass. We can solve that for t. We find that t is, and we leave out the pi's and the 2's, the numerical factors, the t is proportional to mu, the reduced mass, times b times a divided by L. We can take the square of this equation, so then we have t squared proportional to mu squared, b squared, L squared, a squared, and then exploit the fact that b squared, if you remember the definitions of a and b, let me show them to you on the on this earlier page here. Look at the definitions of a and b. Take the square of b, then we have b squared equals kappa squared divided by 1 minus epsilon squared. But kappa divided by 1 minus epsilon squared is a. So in fact, b squared is kappa times a. B squared is equal to kappa times a. And then remember the definition of kappa. Kappa in turn was L squared divided by mu alpha, and this times a. Then you see that the L squared cancels. The mu partially cancels. Here we have a mu squared and then we divide by mu. So this cancels. And what remains is a numerical factor, some numerical factor times mu over alpha times a cubed. At this point, we've never so far wondered about the alpha, but here we really need the Newton's law for the gravitational force. The alpha that appears in the Kepler potential is actually the mass of the planet times the mass of the sun times the gravitational constant gamma. The mu, in turn, that's the reduced mass. Remember the reduced mass, that was mass of the planet times mass of the sun divided by the total mass. But if the mass of the sun is much greater than the mass of the planet, the total mass is practically equal to the mass of the sun. So the mass of the sun cancels out, and the reduced mass is, to a very good approximation, simply equal to the mass of the planet. For mass of the planet much smaller than mass of the sun. So we use these two results for alpha and mu, and then you see in the ratio mu over alpha, the mass of the planet cancels out. And this is approximately equal to 1 over the mass of the sun times the gravitational constant, and then we are left with a cubed. And you see in this factor in front of the a cubed, there's only the mass of the sun and the gravitational constant. There's no longer any parameter that's specific for a planet. So this is constant. It's the same for all planets. And hence, indeed, the ratio of t squared over a cubed is the same for all planets. That is Kepler's law number 3.